students, welcome to this lecture number 13 and it is on modeling of single phase and three phase transformers. Before going to the transformer, let us see what we have seen in last class and then we will go for transformer. In the last class we have seen how to model the distribution lines, and we have seen the pi model and short line models of the distribution lines. And we have seen that the structure of these equations of pi model, they are same as single phase equivalent which you use in case of transmission line modeling. However, here since there are all three phases as well as their shunt admittances of all the three phases are existing, each of these entries they become 3 by 3 matrix. So, here this unity matrix, which is actually 3 by 3 unity matrix, ZABC is matrix of 3 by 3 which consists of your all the line impedances and the mutual impedances between the line. Similarly, admittance matrix is nothing but the 3 by 3 admittance matrix, and we have seen how to get this admittance matrix also in the last class. And in case of short line, we have seen that ABCD mathematics you can get it by neglecting your shunt admittance. In that case, you need to make this admittances to be equal to 0. In that case, your short line model will be just like this, where A and D parameter will be just unity matrix of size 3 by 3, B parameter will be 3 by 3 matrix of your series impedances, and C matrix will be 3 by 3 matrix of zeros. And as I told you, most of the cases will be using short line model because length of distribution line is shorter, and in that case your shunt admittance will be negligible. Let us come back to your transformers. We know that transformers are used to step up or step down the voltages, and in case of distribution system generally it will be step down. So, we know that the subtransmission level voltage we need to step it down to say initial voltage, that is 11 kV, which we say HT line, and then again it is further stepped down to your LT, that is 440 volt or 400 volt 3 phase or 230 volt single phase. So, for this transformation we need transformer, and transformer is very important component, and we have seen that generally distribution system need to be analyzed in 3 phase because most of the cases it is unbalanced and 3 phase analysis is required. So, the connections between the phases or connection between the winding also need to be considered while modeling these transformers. But before going to the actual 3 phase connections, let us see how we can model a single phase transformer. So, we already seen this single phase 2 winding transformer equivalent circuit, we already seen it. Just I want to model it by converting those equations which you are derived for single phase transformer and want to put them into what is called as your ABCD parameter format. So, to put that, let us see this transformer, single phase transformer, 2 winding transformer. We know that there is magnetizing branch. Since it is shunt branch, I have shown it using admittance Ym. Then there is ideal transformer which is having the internal voltages E1 and E2, load voltage VL and then load current I2, and the leakage impedance of the transformer referred to the secondary side is shown it here. This is applied voltage or source voltage Vs, Is primary current, this I1 is primary current after your excitation current or current to the excitation branch. Then NT, we know that E1 by E2. In this case, these are the primary voltage by secondary voltage. Anyway, we can take either way also, but generally I am considering in step down configuration, I am considering it will be voltage on primary side divided by voltage on secondary side. So, again it will be N1 by N2 here, and we are interested in calculating these 4 parameters A, B, C, D, small a, b, c, d, and then there are 2 more parameters I am interested in, that is capital A and capital B, because many times the source voltage is known and we are interested in calculating your load voltages. So, in that case your load voltage need to be written in terms of source voltage and load current. So, in that case this capital A parameter and capital B parameter will be useful. So, we will try to derive the capital A and B, capital B also. Okay, so let us write the equation. So, in this case whatever voltage which is coming across E2, if you multiply it by a number of turns, I will get the voltage E1, and voltage E1 and Vs, they are same because the same voltage is coming to Vs. So, E1 and Vs, they will be same. The voltage across these terminals, which is E2, so E2 will be equal to voltage at load end plus drop which is happening across this impedance. So, it will be VL plus drop which is happening across this leakage impedance ZT into I2 multiplied by number of turns will give me E1, and E1 will be equal to Vs. So, we have this equation here from the first principle. If you take this NT inside the bracket, so it will become NT multiplied by VL and then NT into ZT into I2. Then if you want to write the equation for IS, so if you see this IS is having 2 parts, this excitation current part which will be voltage multiplied by this admittance which is given by this one, and then remaining current which is going into primary winding which is say I1. And I1 and I2 they will be related. So, they will be just NT into I1 divided by NT. So, sorry, I2 divided by NT. So, I can just write I1 is equal to I2 divided by NT, and whatever equation for Vs we have got, we can put here to represent this Vs. So, if you put this Vs equation into this equation, I am getting these 2 terms here, and I am after writing I1 and I2 they will be related by your transformation ratio. So, I2 divided by NT will be your I1. So, in that case separating out the terms which are VL and IL together. So, there is only one term which is related to VL, I am taking this out, and there is 2 terms related to I2. So, if you take them together, I will get this term here. So, here we can easily see that I am writing 2 equations, Vs source side voltage and source side current in terms of load side voltage and load side current. So, basically these parameters which you are getting it here, that is NT, NT into ZT and this NT into Ym and this particular bracketed equation, these are nothing but your ABCD parameter because we are getting this in our required form. So, once you get into required form, so this will become your A parameter, that is NT here, this will become your B parameter NT into ZT, NT into Ym will be your C parameter, and this bracketed term NT Ym ZT plus 1 by NT is your D parameter. And as I told you, we are also interested in calculating this second term here, which is capital A parameter and capital P parameter, which relates source voltage and your load currents. Basically these 2 terms are known. To get that, you can just rewrite this equation in terms of VL. So, in this case, so Vs divided by NT minus ZT into I2. So, basically this will be your required parameter A and this will be your required parameter capital B, which relates your source voltage and load current into the load voltage, because as I told you many times we need to calculate load voltage where your source voltage and load current basically is known. So, this gives me your capital A. So, since it is for transformer I am writing AT and BT. So, this is related to single phase 2 winding transformer. Sometimes these single phase 2 winding transformers may be having auto transformer kind of configuration, and we can easily derive the ABCD parameters for auto transformer kind of configuration by knowing the equations for single phase transformer. So, in this case, say let us see the same, or suppose this same single phase transformer is connected like auto transformer configuration, which is shown like this, means basically this terminal here is connected, basically connected here. This terminal is connected here, and in that case configuration will become something like this. So, in that case your new turns ratio, so primary turns will be again N1 because the same primary voltage is getting applied across this one, and secondary terminal we are taking X1, and load is we are connecting between your X1 and H2. So, basically load is getting connected between this terminal and this terminal here. So, if you are connecting like this, then total turns which are coming across load side will be this N1 turns plus your N2 turns. So, in that case your turns, which primary turns are N1 and secondary turns are actually N1 plus N2. So, I can just divide denominator and numerator by N2. So, this will become your turns ratio NT of same transformer having two winding configuration. So, and this will become 1 plus NT. So, this is my new turns ratio if you connect the same two winding transformer into auto transformer configuration. Now, you can easily calculate ABCD parameters for this transformer. Just what you have to do is, in this case it is A parameter is just NT, it will become A parameter, new A parameter will be NT new, which is basically this term here. B parameter we have seen it is NT into ZT, in this case it is NT new into ZT. C parameter is NT into YM, here in this case NT new into YM, and here also this NT will get replaced by your NT new. So, this is how we can get the auto ABCD parameters for auto transformer kind of configuration. So, this is about single phase transformer. Now, let us go to the 3 phase transformers. So, there will be most famous configuration which is grounded Y by grounded Y connection. So, Y connection which is having both side ground connection. Now, this I am representing it, or you can say this neutral is grounded here. Then primary voltages, basically phase to ground voltages or phase to neutral voltages, they are VAN, VBN and VCN, which are represented here, and then there are line currents IA, IB and IC are written here. However, to write them in compact form, since these voltages are line to neutral voltages, I am writing them as all the 3 voltages as voltages line to neutral, and all the 3 means ABC. So, that is why these 3 terms I am just writing VLN ABC, and capital terms I am using because they are primary side, and all these 3 currents I am writing IABC. So, this basically this all the 3 current represent your IABC. Similarly, on your secondary side, the again it is, since it is a ground connection, the voltages I can write them in terms with respect to neutral. So they will be VAN, VBN, VCN, IA, IB, IC will be line current, and collectively I can write this line to neutral voltages, and for all the three phases, so I am writing VABC. So these three terms will be written as VLN ABC, and these three currents will be just IABC. So this is actually representation of voltages and currents if there is star connections on primary and secondary side, or maybe primary side or secondary side. Let us say if there is delta connection, for this case I am considering delta winding, so there will be no neutral. So in that case we can represent them using line to line voltages. So there will be VAB, VBC and VCA, and then there will be line currents IA, IB and IC, and secondary side also it is, since it is delta, there will be VAB, VBC and VCA voltages. So these three voltages, line to line voltages and your line currents. Now this line to line voltages I am writing VLL, earlier I have written VLN, so in this case VLL. So all the three voltages are VLL, capital ABC. Since they are line currents, so this will be just IABC, and here also this is VLL small ABC, all the three voltages, and then this is your IABC, line currents. Okay. So since this is delta connected kind of transformer, so there will be delta currents, means these currents will be get divided into delta windings, which will be like this. So say it's phase connected here, and then this C phase is connected here. So let us say the delta currents are flowing like this. So this will be your ID AB, this will be your ID BC current, and this will be your ID CA. So these currents are, three currents are like this, and collectively these three currents are written as ID ABC. Basically they represent your delta currents. Similarly on the secondary side, ID ABC, they are basically three delta currents which are represented by these three terms, and these small letters A, B, B, C and C, as I told you, they represent your secondary side, and capital letter represent your primary side. So this is actually representation of various voltages and currents in star connections and delta connections. If the winding is say delta and grounded Y, so some transformers say primary side is delta and secondary side is grounded Y, then your terms will be, these terms will be on primary side and these terms will be on the secondary side. So this is actually representation. Now in this case, in three phase transformer also we are interested in calculating these ABCD parameters. So as I told you, once you know the ABCD parameter, you can write them in any terms, or it is easy to get whatever quantity which you want in either any side, means source side or load sides, quantities can be easily calculated if you know the ABCD parameters of your component. So in this case also we need to put this three phase transformer into ABCD parameter format. So in this case, since in single phase we have seen that there is 1 by 1 entries, however in three phase transformer all these A, B, C, D parameter, they will be 3 by 3 size matrices. So these line to neutral voltages and line currents of primary side and line to neutral voltages and line current on secondary side are actually linked by your ABCD parameter. So all the for all the configurations, like we know that there are many configurations, so there might be grounded Y delta transformer or delta transformer or just Y transformer. So there are many configurations. So for each of the configuration we need to bring those equation into this format, so that we can use them in any analysis like short circuit or load flow analysis or state estimation. And one more thing is that we also find out this capital AT and capital BT matrices, because many times we need to know load voltages in terms of source voltages and load currents. Let us see some terms which are related to different derivations for different configurations. Before going to this configuration, let us define some terms. So, here I am defining turns ratio. The turns ratio is defined, we are defining, or we are using the terminology that voltage, rated voltage on HV side divided by rated voltage on LV side, I am calling it a turns ratio. So, in case of say delta star transformer, the voltage across primary winding will be line to line voltage, and voltage across secondary winding will be line to neutral voltage. So, while calculating NT for delta star configuration, we need to take the ratio of line to line voltage on HV side divided by line to neutral voltage on LV side. However, if you see star star connection, you can take line to neutral voltage ratio on HV side and line to neutral voltage on LV side. So, this is your turns ratio is defined NT. Then in all the configurations, I am referring these leakage impedance of your transformer on secondary side. So, I am taking on the secondary side or low voltage side and connecting it together, and the matrix of it is actually ZTA, ZTB and ZTC are the diagonal entries which are corresponding to A phase, B phase and C phase. If it is delta connection, this impedance may be between two phases. In that case, I can say ZTAB, ZTBC, ZTCA. So, wherever particular configuration is coming, I will explain that. So, these are the three impedances of three transformers in three phases. Then the winding voltage ratio. So, basically the voltages across the windings are always related by your turns ratio. So, the voltage VAG here and VTA, they will be always related by your turns ratio. Similarly, VBG and VTB and VCG by and VTC, they will be related by turns ratio. So, this turns ratio will be again 3 by 3 matrix, which is having configuration like this, where NT is your diagonal entry, and this particular matrix I am calling matrix AV, voltage ratio, which basically relate terminal voltage of secondary to the primary voltages. Basically, this is related to voltages across the winding. Similarly, winding currents will also be related to turns ratio, means current which is going inside winding and then which is going opposite, I can say. So, current which is going in and going out of the winding, they will be also related by turns ratio. However, it is in opposite direction. So, primary current will be just 1 by NT times IA. So, in that case, we are defining this matrix AI, which is having diagonal entries 1 by NT, and in that case your equation will be like this. So, this AI and AV, basically we can call them as a transformation matrix, which basically transforms the voltages and current. So, AV I am using it for transforming the voltages, terminal voltages, and AI I am using for transforming winding currents. Now, many times in all those configuration, what we need to do is, in case of voltages, many times we need to control, we need to convert line to neutral voltages to line voltages and vice versa, means line to line voltages to line to neutral voltages. So, those transformation matrix also need to be known. It is since it is not balanced system, they will not be just related by root 3. So that's why in this case we need to get those matrices. Since it is, we are considering totally unbalanced kind of system which is having all the types of current, positive sequence, zero sequence, negative sequence. So let's see first conversion, that is line to neutral to line voltages. So if you want to convert line to neutral to line voltages, so we know that line to line voltages VAB we can write is VAN minus VBN. Similarly VBC, VBN minus VCN, VCA will be VCN minus VAN, and if you write them in matrix format, on this side it will be all these line voltages, and on this side there are line to neutral voltages. So these line to neutral voltages we want to convert into line voltages, and in that case your conversion matrix will be this one. So basically all these three equations I have just written into matrix form, means VAB will be just VAN minus VBN, like this. So as I told you, your line to neutral voltages will be converted into line voltage using this T matrix which I have calculated it here. Now suppose you want to calculate line to neutral voltages, and line to line voltages are known, means I want to calculate VLN ABC, and then it will be equal to some matrix here multiplied by VLL ABC. So I want to convert line to line voltages to the line to neutral voltages. So actually you may think that it should be D inverse. So if I put D inverse, it will automatically convert. However, this D inverse, if you see, it is non-existent. If you take the inverse of this D matrix, it actually comes infinite because it is singular matrix. So we cannot do that way because this D inverse is non-existent, which will come infinite. So in that case we need to find out how we can convert, means what will be this matrix here. I'm calling this as say W matrix, and we want to find out what will be this W matrix which converts line to line voltages, unbalanced line to line voltages to line to neutral, unbalanced line to neutral voltages. So to convert your line to line voltages to line to neutral voltages, we have seen this W matrix. However, we want to get this W matrix here. So we can get this W matrix from these following relations. So we you have to use sequence component theory to get this W matrix. So we know that according to sequence component theory, we can convert these phase quantities into sequence quantities using this transformation matrix here. So phase voltages VAB, VBC and VCA will be converted into, because these are line to line voltages, they will be converted into line to line zero sequence voltage, line to line positive sequence voltage and line to line negative sequence voltage. And since these are nothing but line to line voltages, I can, in short form, I can write VLL 012 and this will be VLL ABC. So these are the sequence components, these are nothing but phase components of the voltages, and this is your transformation matrix. So in short form, VLL 012 will be nothing but AS inverse, where this is your AS matrix multiplied by VLL ABC. So this is nothing but phase domain voltages, and we know that this AS in transformation matrix is given by one angle 120 degree, and in that case your AS inverse will be one angle 240 degree. Similarly, we can get sequence components of line to neutral voltages. So your this line to neutral voltages in phase domain will be written like this. So these are the line to neutral voltages in phase domain. these are the line to neutral voltages in sequence domain. So 0, 1, 2, and these are nothing but your conversion matrix, which is given by, again it will be same matrix here. So I can write these equations into short format, which is VLN 0, 1, 2 will be equal to AS inverse, this is your AS inverse matrix, and VLN ABC. So this expression in short form I can write it like this. We can actually again write this equation like this by taking this AS inverse on this side. So in this case VLN ABC phase quantities will be nothing but AS matrix multiplied by VLN 0, 1, 2. So here we are converting your sequence quantities into phase quantities. So we have got these two relations here. I can say this is relation number 1, this is say equation number 2, and third equation we can get it from relation between line to line sequence component and line to neutral sequence voltages. So this is nothing but line to line sequence voltages and line to neutral sequence voltages. So this is line to neutral 0 sequence voltage, line to neutral positive sequence voltage, line to neutral negative sequence voltage. Similarly, this is line to line 0 sequence voltage, line to line positive sequence, and line to line negative sequence. And these are related by this transformation matrix, which I am calling T. So if you see these entries here, 0 sequence components in line to neutral as well line to line, they are same. If you see line to neutral voltage and line to line voltage in positive sequence, they are related by this TS star, which is represented by this, and this can be easily understood by this positive sequence figure here. So you can see that in positive sequence this is your VAN, VBN, VCN. So these are positive sequence, and if you calculate line to line quantities, so VAB will be nothing but VAN minus VBN. So this will be nothing but minus VBN, which will be written like this, and so if you add them together it will be nothing but VAB here. And if you see the phase angle difference and magnitude difference between these two quantities, so in positive sequence your line to neutral quantities will be 1 by root 3 times of line to line quantities, and phase angle will be lagging with respect to line to line quantities. So that's why here we are getting TS star, which indicate the line to neutral quantities are lagging behind line to line quantities by 30 degree. Similar way, in case of negative sequence, we can see that VAN here, VBN here, because it is rotating in opposite direction, and VCN is here. So in this case, if you calculate VAB, which is basically VAN minus VBN, so this is minus VBN here, and if you add them together it will be your VAB. So in this case, in case of a negative sequence, you can see your line to line quantities are lagging behind your line to neutral quantities, or we can say line to neutral quantities are leading with angle 30 degree with respect to line quantities. So that's why to represent this leading 30 degree angle of line to neutral quantities with respect to line quantities, we represent by TS. So transformation matrix which convert your line to line sequence quantities to the line to neutral sequence quantities is given by this matrix T here, and this matrix T is nothing but this matrix here, whose TS and CS star is given by these relations, and I am calling this relation as expression number 3, and these 3 relations, 2 on last slide and this one I am taking on this slide. So this is your expression 1, this was your expression 2, and this was your expression 3, which you got on last two slides. And from these two relations, by putting this VLN 012 here and writing this expression here, I can get VLN ABC will be equal to AS multiplied by T multiplied by VLL 012. So, AS multiplied by T multiplied by 012. Then this VLL 012 I can put here from this expression number 1, and in that case it will be AS inverse multiplied by V line to line ABC. So, VL ABC. So, here we get line to line quantities, phase quantities on right hand side, and line to neutral phase quantities on left hand side. So, we have converted these line to line quantities into line to neutral quantities using this matrix transformation here, and that is represented by W. So, W will be nothing but AS multiplied by T multiplied by AS inverse, and if you explicitly calculate that AS multiplied by T multiplied by AS inverse, you will get this matrix. So, this W matrix will be given by this expression here, which converts your line to line voltages to the line to neutral voltages, where AS, AS square, TS and TS star are given by this expression. So, in summary of today's lecture, we have seen modeling of single phase distribution transformer. Then we have seen how we represent voltages and currents during modeling of 3-phase distribution transformers, and for that we need various conversions. Two conversions in case of voltage we have seen, that is line to neutral voltages to the line to line voltages, and line to line voltages to the line to neutral voltages. And we have seen that in case of line to neutral voltages to the line to line voltages, we have this matrix D, and which you derived. D matrix is given by this expression here, and to convert line to line voltages to the line to neutral voltages, we have this W matrix, and W matrix will be given by this expression here. In the next class, we will see a current conversion and few transformer models. Thank you.